Hello fellow problem solvers, so today we're doing a geometry lemma, geometric lemma 2, that you could use in some introductory geometric problems. And I think it's a cute little lemma. I suggest you try it out for a minimum of 5 minutes, ideally 15 minutes to 45 minutes, but not more than an hour and a half. This is a great problem if you're doing introductory level geometry, you're trying to build up some level of skill in geometry. This is one of the first lemmas I learned when I wasn't that good in geometry. Actually, one of the first lemmas, but that was like after a year or more after doing geometry, even more so than a year. So this is the lemma. Let H be the orthocenter center of the triangle ABC. X and Y are the reflections of H with respect to the side BC and the midpoint of BC respectively. Prove that X and Y lie on the circumcircle of the triangle ABC. It's a cool little thing. Now let's try to solve it. I invite you to take 5 minutes, draw the diagram, do some angle chasing, and see what you have. And now without further ado, and also, when you try that out, see if you can figure out if there's anything special holding for either X or Y, or maybe both of them. That's up to you to figure out. And now let's go to the next step. And here's our diagram now. So what do we have? We have H, I took D to be the what's it called? AH intersect BC is D. This is M is the midpoint of BC, X and Y. We don't know that these are on the circumcircle just yet, so let's delete this a bit. And now, what are we going to do? Well, we have reflections. Let's do some angle chasing. So the first question is first. Let's start with X. What is enough for us to prove? I invite you to take 2 minutes to figure that out. And the answer is this. What is enough for us to prove is that BXA is BCA. So it's enough to prove that this angle right here is gamma. Now, my question for you is, take a minute. What is the angle BXA equal to? Do we have it from something? Given this is a reflection in BC. Do we know what that is? Take 2 minutes to figure that out. And the answer is this. The answer is this angle right here is equal to this angle right here. Why? Well, there's many ways we can go about this. An easy way to think about it is, what is a reflection? A reflection is you have a point, and you do reflect it. I mean, you reflect it here. Great. That was a phenomenal explanation. But in reality, what happens is, it means that this point, once you reflect it over a side of, or it's reflected over a line, that means that the other point is equidistant. That it means if you take any other point on this line, then that point is equidistant to this one and its reflection. So here that means that BX is equal to BH, right? So, and what does that give us? Well, that gives us that BXH is isosceles. But also, we also have in general that, say, BHM and BXM are also identical. And you can think of that as you have two isosceles triangles. One is like this one, HXM and HBX. So these are like two isosceles triangles you have, and that's how you can go ahead and prove these things. Now, here, what does this mean? We need to figure out what this angle is. So what is the angle BHD? Well, this angle is going to be 90 minus this angle. And what is this angle? Well, this is a 90-degree angle, so this angle right here is 90 minus gamma, which makes this gamma, which means this is gamma. And so these are the X lies on the circumcircle of ABC. Another way we could have figured that out is using the sort of reflection thing. What is the angle BXC? Well, because X is a reflection of H, in terms of, with respect to this line BC, we have this is equal to BHC. Now what is this? It's 180 minus alpha. And this is just when you get used to dealing with the orthocenter, so a lot of problems with the orthocenter, circumcircle, the incircle, you will remember these angles by heart. You don't need to memorize these things. You can always, actually never memorize these things. Always learn how you can figure them out from the first principles, just by saying this is alpha, gamma, beta. Okay, now I can calculate everything and get to the solution. So it's usually you don't want to memorize all the angles, just you want to have a way that you can get to them always. Sure, memory is good, but it's not important, it's not necessary. The more important thing is that you can get to it. Yeah, I'd say so actually. And now, so we have x. Anything special about x? No, nothing really that I see at the moment. So what about y? Well, this is actually pretty cool. So when you reflect a point with respect to another point, that only means that this is a point such that my is mh, and yeah, that's pretty much it. and that these like 3 points are on the same line. That's what a reflection with respect to a point means. Now, what does this give us? Well, what do we know about x? I know it's wacky. We know about x. I mean, there's many ways to go about this. One way is, I mean, I just saw now what we know about x, and I just thought it was much cooler than what I initially planned. What I initially planned to tell you is like, hey, we have m as the midpoint of BC, midpoint of HY. Ergo, what we know by this sort of side angle side theorem, that these two are congruent. So then we have the angle CYH is equal to this one. But more importantly, we have YCB. The angle YCB is equal to this angle right here. So we have this angle is going to be equal to 90 minus gamma, if I am not mistaken. Actually, yeah, this does not solve our problem initially, just yet. Actually, it does. It does actually solve our problem. So what do we get? Then we get that YCA is 90, because this is 90 minus gamma plus gamma. And analogously, we'll have these two are congruent, these two triangles. And we'll get that this angle right here, YBC, is going to be 90 minus beta. 90 minus beta because this one is 90 minus beta. And so this is 90, 90. They sum up to 180, ergo we're done. However, that is not what I wanted to show you. This is cool and all. The thing I want to show you with this point y was that it's like A, O, and Y, where O is the circumcenter, are collinear, because this is 90, and that's pretty cool. But there's another thing. I feel like a salesman. Wait, there's more. There's a thing that we could have done also here, which I just think is beautiful. So we know that these points here are, collinear, and MH is MY. What is also MH equal to? Take a minute to figure it out. Well, it's equal to MX, because X is a reflection of H with respect to line BC. What do we know about X? It's on the circumcircle. And we now also know that MX is MH is MY. Now what does that give us? By pure angle chasing, if you call this angle phi, then this is phi, then this is 2 phi, and then this is 90 minus phi and 90 minus phi. In other words, the angle HXY is equal to 90. And now with that, we have HXY is 90, which means YXA is 90. Oh, I thought actually we were going to be done with this. It turns out we're not. However, is there hope for us to be done? Okay, there is hope for us to be done, but it's actually more complicated. I just thought this was much cooler because we get this like YXA is 90. We also need YCA is 90 or YB is 90 to actually finish up. We can get that in many ways. One is like doing the thing that we did previously. Another way, which I also think is kind of cool, kind of interesting, is what is enough for us to prove is that like these 4 points are in the same circle. And because this here is 90 and this is 90, that means XY is parallel to BC. So what is enough for us to prove is that this thing, like this is already a trapezoid, BCYX, it's enough for us to prove that it's an isosceles trapezoid. And the reason we have that is because the midpoint of BC is equidistant from X and Y. How can I then prove that this is the case? I'm actually not sure. So how would we go about proving this now? Well, we can definitely use some either phantom points or similarity to prove that, like if you have the midpoint is equidistant from these two. Maybe that's a problem that you want to try out and post it out in the comments below. How do you know if you have like this sort of trapezoid BC? So it's BC, YX, and you have the midpoint. You have BC parallel to xy, and you have mx is equal to my. Can you prove that bx is equal to cy? I think it's a cool problem. You need to prove that this angle is equal to this angle. Oh wait, actually it's not a difficult problem. You try to do it. Take 2 minutes and try to actually do it now. Here's the solution. I mean, this is equal to this, because this is equal to this. Mx is my, so this angle is equal to this angle. And because of this, these two are parallel, that's why they're both equal to this angle. And then we have side angle side, and bam, we're done. This finishes up our geometric lemma 2. It's a cool little lemma. You can find it in some problems. Sometimes, you will have x defined as, like usually what problem makers do, and I've created a geometry problem once that actually went to a competition, is you'll try to hide points. You'll try to define it in a way that's not useful. That's how you sort of can make it more difficult. For example, if you want to use the fact, if the problem uses the fact that x is on the circumcircle of ABC, you will define x in terms of h being reflected over BC. If you want to use the fact that if you need to use the fact that bx is equal to bh, you'll define it as the intersection of AH and the circumcircle. It's usually how you will go about doing these problems. Or maybe not even AH, maybe you hide H and you say, let the height from A intersect BC, let the height from A intersect the circumcircle of ABC at point X. And then you've hidden point H entirely. And maybe you need H to use in the problem. So that's how these things are used in problems when you're making them. And this solves our lovely little problem. And the interesting part is that xy is parallel to BC, and y, o, and a are collinear. Like ay is the diameter of the circumcircle. And this finishes up our problem. And as always, thanks for problem solving.